Hello.
Hello, hello. Can you hear me?
Yeah.
Okay.
Okay. So we'll begin with something that we did not discuss completely in the last class, inverse, right? So inverse of a number modulo p. So we say that let p be a prime and a is an integer that is co-prime to p, right?
Yeah,
Then we said there always exists x such that ax is congruent to 1 mod p, and this x is called inverse of a. Inverse of a, and sometimes written as x is written as a inverse or 1 by a mod p. Now the question was, how can we be sure that there is always an x, right?
yeah,
So that was the question that we did not solve last class. So how can we be sure? Actually, there is a very easy way to be sure. We did not think of that in the last class. So here we are saying a is an integer co-prime to p. So GCD of a and p is equal to 1, right?
yeah,
So by Bizot's identity, we can say that there are two numbers x and y such that ax plus py is equal to 1.
yeah,
X and y are integers.
yeah.
Now you take mod p on both sides. This mod p will be 0, right?
Oh, yeah,
So this is like one step only, right?
yeah,
Because this is mod p will be 0 and you are getting ax mod p is 1 mod p, right?
yeah. And
So then x is that integer. So the only thing that matters here is GCD of A and P is 1. If you have that by Bezot's lemma, you have this, and then you get this, right?
yeah,
So one thing to know here is once you know inverses, inverses are very convenient sometimes because they inverses behave like normal fractions. So what we will see is you will have properties like this. Let B and D is not congruent to 0 mod P, then for every A comma C, we have A by B plus C by D. Like right now we are writing it as fractions, but what we mean by this is actually A B inverse plus C D inverse, right?
yeah.
And that will be equal to the way we add fractions, it will be AD plus BC by BD, right?
Yeah. So it's actually B inverse times D inverse.
So this is this, right?
Yeah,
So AB inverse plus CD inverse is actually equal to AD plus BC multiplied by BD inverse, which you can prove easily by taking it inside AD into BD inverse plus BC into BD
oh,
inverse, right?
so so we cancel D and B.
Correct, right?
Oh yeah, but the left hand side, oh yeah. Oh, there's a bracket.
There's a bracket here, right? Correct.
Yeah, yeah,
You should get the same thing because you're getting B inverse, D inverse. And here you're getting A D inverse, and here you're getting C D inverse, right?
Yeah.
Correct. So actually, you can just add it like a fraction, even though what you mean is this: A into B inverse plus C into D inverse, right?
Yeah.
Similarly, you can also multiply like a fraction. A by B into C by D is same as A B inverse multiplied by C D inverse. And that is the same as AC multiplied by BD whole inverse, or AC by BD mod B. Okay.
Okay.
So these inverses will come in handy because we will use them to prove Fermat's little theorem and Euler's theorem and all. For now, let's look at a question first and then we'll see. Question is this: find the last three digits of 2005 to the power 11 plus 2005 to the power 12, so on till 2005 to the power 2006. There is no shortcut solution for this, so you'll have to try a little bit. One thing to keep in mind is that last three digits means you have to do mod of 1000.
Okay.
You should note that 2005 is
Yeah. It's
5
fine.
mod 1000. And so all of these can be written as 5 power 11 power 12 is 5 power 2006.
Is it answer 850?
The answer is 500. Just
Huh?
check. Maybe you have made some mistake somewhere.
No, maybe. Because I found that if the power is an odd number, it should be 125, and if it's even, it's 625.
Correct. So it is the 625, 125, and so on, right?
Yeah.
But then you are counting the terms slightly wrong, I think. So the total number of terms are 1996.
Yeah, then there should be 998
Uh,
625 and 998 125.
Correct. So finally it will be 998 into 750, right?
Yeah.
And
Oh,
you have
oh
to
yeah,
do
yeah. I forgot to add a zero because I timed 75.
correct.
I forgot to add a zero at the back.
Yeah, yeah. So if it is mod 1000, you can say that this is minus 2 mod 1000, right?
Yeah.
And this is minus 250 mod 1000.
Yeah.
So it will be 500, right? Correct.
Yeah.
Or you can multiply and get it also.
Yeah.
One more question. If A and B are two integers such that 11 divides A square plus B square, show that 121 divides A square plus B square. 11 divides A square and B plus B square can happen in multiple ways.
Yeah.
One way is if 11 divides A square, then 11 must divide B square, right?
Yeah.
So that means that 11 divides A and 11 divides B,
Yeah. And
right?
yeah.
So that will mean that 121 will divide A square and 121 will divide B square. So
Yeah.
121 will divide A square plus B square. So that is the easy case, right?
Yeah.
The other situation is slightly more complicated when it is possible that 11 does not divide A square or 11 does not divide B square, but it divides the sum.
Yeah. I don't even know how to start.
So start by saying that, okay, 11 does not divide A square or B square. So we know that 11 does not divide A, right?
Yeah.
So A can be written as some congruent to K mod 11, right?
Yeah.
A leaves a remainder K when K can be going from 1 to 10. right?
Yeah.
So therefore, by property of congruence, we have a square is congruent to k square mod 11, right?
Yeah.
And this k square can be called as L mod 11, and L can be what? Let's let's
1.
square these and see what are the possibilities, right?
Yeah.
So 1 square is 1, L can be 1, it can be 4, it can be 9, and when you do 4 square 16, it becomes 5, right?
Yeah. Then 3.
5 square is 25, so 3. 6 square is 36, which is already
Yeah.
36 is
Also 3.
3. Huh. And 7 square is 49, which is 5, which is already there. 8 square is 64, which
9.
is 9.
Yeah.
And 9 square 81, which is
4.
4. And 10 square 100, which is 1, right? So L can be this, right?
Yeah.
So A square is coming out to be 14953, right?
Yeah.
So similarly, B square, in the same manner, B square will be M mod 11, which will also be 14953 only, right?
Yeah.
Correct. Because there is no difference between A and B. Like the same thing will work for B square also, right?
Yeah.
Now, A square plus B square will be L plus M mod 11, right?
Yeah.
And let's see what it is coming. L plus M mod 11. So, but we know that
Oh, yeah. There's no sum that is a product of 11.
there is no sum that,
Is 11 or a product of 11.
uh,
Is it? I mean, like 1 plus 4 is not 1 plus 9, 1 plus 5, 1 plus 3, then 4 plus
uh,
9, like
there is
that.
nothing that is coming, right?
Yeah.
Nothing that is coming 0 mod 11.
Yeah.
3 plus 3, 3 plus 5, 3 plus 9. Nothing is coming, right?
Yeah. So uh,
So,
it's impossible.
so L plus M is never coming 0 mod 11, right?
Oh, yeah.
So that means A square plus B square can never be divisible by 11 in this case, right?
Yeah.
Correct. So the only way it can happen is this case then, right?
Yeah.
So 11 divides A square plus B square means this must happen. This cannot happen, what we thought here. This case didn't work out, right?
Yeah.
And in this case, it is very easy to prove that 121 divides A square plus B square, right?
Yeah.
Okay, so basically what we did here was just tried it out. Like since we are assuming that 11 is not dividing A and all, then we took some K mod and tried it out and saw what happened. Like there's no tricky way or clever way to do it. It's just a little bit of work you'll have to do and see.
But like if we replace 11 by other number,
It
will
might
it?
not work like this then. Like it is not necessary that it is working out only for 11 this thing. Maybe with some other number, maybe some non-prime number, it might happen, right?
Yeah.
Not sure whether this property is true for all primes, but maybe. Uh, the next one is this. Show that if the the square sum of the square of two whole numbers is divisible by 3 is divisible by 3. Okay, so this is proving the similar property. Each of them is divisible by 3. This is proving a similar property to the previous question, I think. You have to show that if the sum of squares of two numbers, two whole numbers, is divisible by 3. So 3 divides x square plus y square, right?
Yeah. So
Then prove that 3 divides x and 3 divides y. Right? Something similar to the previous property.
this is easy, right? Just like it's 1, 2 or 2, 1. But like
Yeah.
the square is all 1.
Correct.
All congruent to 1 more 3. So it's
Yeah.
impossible.
So this is easier because it is only 0, 1, 2, right?
Yeah.
So you can say that x can be 0, 1, 2 mod 3. So x square will be 0,
Or 1.
1 mod 3, right? And similarly, y square will also be 0 or 1 mod 3, right?
Yeah.
So if the sum of the squares we have to do, sum of x square plus y square will either be 0 or 2 or 1, right?
Yeah.
0, 1, 2 mod 3, right?
Yeah.
And if it is divisible, that means it is this case, right?
Yeah.
And this case means it was 0 here and 0 here, right?
Yeah.
So basically x and y must be divisible by 3. Only then that can happen, right?
Yeah.
So this one was easy. In general, can we say something? No, I don't think we can make any claim right now. Okay, let's go on to some theory. So let's look at this. So we will define a set S called, we have already discussed it a little bit, I think. It is the reduced residue system modulo n, which is basically the set of remainders possible when you divide any number by n, right?
Yeah.
Set of possible remainders. So in general, it can be from 0, 1, 2 till n minus 1, right?
Yeah.
Now, what I want to say is, let's say you pick two numbers, A and P, where P is prime and GCD of A and P is 1. A and P are co-prime, P is prime. Now, what you want to prove here is A into S would be congruent to S mod P. So where S is basically the reduced residue system modulo P. So S will be the set 0, 1, 2 till P minus 1, right?
Yeah. So I want to say is like, well, what does this mean? A times S.
What this means is, if we construct a new set A times S, right? That set will be 0, A,
Or 2.
2A till P minus 1 into A, right?
Yeah.
What we want to say is that this set is equal to this set, right? If you do mod P.
Okay.
Why will that happen? We can prove this, but first let's understand how. Let's take an example and see if it is working out or not, right? So if we say, let's pick A and P such that they are co-prime. So let's say A is equal to 4 and P is equal to 7, right?
Yeah.
So the set S for 7 is what? 0, 1, 2 till 6, right?
Yeah.
And set 4 times S is 0, 4, 8, 12, 16, 20, 24. And if I do mod P here, see what will happen. This set will become 0, 4,
4,
1, 5, 2, 6, and 3, right?
yeah,
Now see, the order has changed, but the set is the same, right?
yeah,
The numbers have rearranged, but it's the same set, equal set, because all elements, number of elements is also same and all elements are identical, right?
yeah, yeah,
So this situation will happen in general, like as long as your A and whatever n you have chosen are GCD is 1, right?
yeah,
As long as GCD of A and n is 1, you will always be able to prove that AS is equal to S mod n. Okay. Now, to do a proper proof of this, you can say that, first of all, look at the two sets, the set S and the set AS. You can see that obviously the number of elements of both sets is same, right?
yeah,
So number of elements is same. Now we have to prove that these elements are also going to match once you do mod P, right?
yeah,
So what we can say here is uh, none of here we had P minus 1 elements, and here also we had P minus 1 elements, right?
key elements, right?
P elements. P elements here also and P elements here also, right?
Yeah,
So if I have to prove that AS set is the set of remainders that come when we do mod P, I need to show that none of these elements is 0 mod P, right?
oh, yeah,
Like if there are P elements and none of them is 0 mod P, then obviously they will be the other remainders that are possible, right?
but like, can we show that none of them are identical?
None of them are identical. That is assured because they are different multiples, right?
Yeah,
So what I want to show is that the difference between any two, right? Like
yeah,
let's say one of them is IA, one of them is JA, right?
yeah,
I and J are two integers that go from 0 to n minus or p minus 1, right?
yeah,
Correct. These two are, what you are saying, these none of them is identical.
yeah,
None of them is identical mod P, right?
yeah,
Because if they're not identical, then there are enough remainders that it has to be the complete set, right?
yeah,
It's like the pigeonhole principle, right? Like if you have enough number of elements and none of them is identical, then it must be this set only,
yeah,
right? It is not repeating inside. So we can say that the difference of these two, if they are identical, assume they are the same some k mod p, right?
yeah.
So take the difference, it will be I minus j a should be 0 mod p then,
Then I minus, oh, yeah, I know.
right? And a and p have no common factors, right?
Yeah, so,
So an I minus j is less than p, so it cannot be divided by p, right?
yeah,
So here we know that P divides I minus J into A, but P cannot divide A and P cannot divide I minus J also.
yeah,
So it's a contradiction, right?
yeah,
So none of the remainders here will be identical and there are P remainders. So they must form the residual class here, right?
yeah,
So that is the proper way to prove this. And once we have the proof here, that AS is congruent to S mod P, we can now use this proof to get things like Fermat's theorem and stuff. So Fermat's theorem, what we will do is let P be a prime. Let P be a prime and consider S is equal to the set 1, 2 till P minus 1. Right? These are the set of non-zero remainders modulo P. Right?
Yeah.
Let A be any integer co-prime to P. Any integer co-prime to P. Right? Then we have AS should be equal to S mod P. Right?
Yeah.
AS is the set obtained by multiplying each element here. AS is the set A, 2A, 3A till P minus 1A, right?
Yeah.
So now if these sets are identical, then the product of these mod P will be equal to the product of these mod P, right?
Yeah.
Because they are identical. So A into 2A into 3A multiplied till P minus 1A should be congruent to 1 into 2 into 3 till P minus 1 mod P,
Yeah.
right? And this part becomes A power P minus 1 and P minus 1 factorial is congruent to P minus 1 factorial mod P, right?
Yeah.
And we know from properties of congruence that you can divide both sides by the same thing as long as whatever you are trying to divide by is co-prime with P, right?
Yeah.
Like we saw the property that AX is equal to congruent to BX mod P. You can divide by X if you want, but as long as
Oh.
P and X are co-prime.
Yeah.
If, right?
Yeah.
So we know that P minus 1 factorial and P have no common factors
Yeah.
because P is a prime,
And
right?
they are smaller than P.
And this has all the numbers smaller than P and P is a prime. So there's no common factor, right?
Yeah.
So we can divide this and remove this and we'll get A power P minus 1 is congruent to 1 mod P, right?
Yeah.
And this is the result, which is Fermat's theorem. And you can multiply by A on both sides and get A power P is congruent to A mod P. That is also another way to say the same thing, right?
Yeah. Yeah.
So this is Fermat's theorem. Now we can also get, using properties of inverse, we can also get something called Wilson's theorem. So we'll see that now. You have understood this, no? How we got this?
Yeah.
Okay. So Fermat's theorem is sometimes used to find out if a number is prime or not. Okay. So for example, uh, suppose you have a doubt whether some number P is a prime or not, right?
Yeah.
Like you want to test some big number is there, you want to test whether it is a prime or not. You can check, you can get any other number A that is co-prime to that P, right?
Yeah.
As long as A is co-prime to P, this result must be true, right?
Yeah.
If you are raising A power P minus 1 and it is not coming 1 mod P, then it is not, P is not a prime.
Yeah.
So remember what are the conditions that are applicable to Fermat's theorem. You have to have GCD A and P should
It's
be
one.
1. You should have P is a prime and then A power P minus 1 is congruent to 1 mod P.
But Euler's theorem is Fermat's theorem's generalization, right?
Euler's theorem's special case is Fermat's theorem. Euler's theorem is that totient function. That one. The special case of that is Fermat's theorem because this phi of p, we will see phi of p is p minus 1. In general, phi of n is not p minus 1. So later we will see Euler's theorem. Fermat's theorem is a special case of Euler's theorem.
Okay.
Okay.
Yeah.
We will discuss that. But for now, just remember that these two conditions are essential. Then you have this, right?
Yeah.
Okay. Then using properties of inverse, we will derive Wilson's theorem. So for example, what we know is suppose A is congruent to B inverse, let's say mod B. Then you can easily show that A inverse will be congruent to B mod B. This
Yeah.
can be shown. Okay.
Like this one-to-one like correspondence.
This is a one-to-one correspondence only. So basically I'm saying if A is equal to B inverse, B is equal to A inverse. Okay. As long as you have the same mod B, right?
Yeah.
So now let's look at an example for instance. So let's say you have the set S, which is 1, 2, 3, 4 till 10 mod 11, right?
Yeah.
Now in this S set, what we can do is we can pair up the numbers which are inverses of each other. So for example, 1 and 1. 1 is the inverse of itself because
Oh,
AX is congruent to 1 mod 11, right?
yeah.
So if A is 1, X will also be 1, right?
Yeah.
Correct. A and X are inverse of each other, 1 and 1, right?
But can we show that the like 2 to 10 there's no ones inverse?
Uh, no. So for example, we will say that 2's inverse will be 6, right?
Yeah, I
We will
know.
get other pairs like 3's inverse will be 4, 5 inverse will be 9, 7 inverse will be 8 when you're doing mod 11, and 10 inverse will be 10.
But I mean, can we show that there's only one inverse of each number in
Can
the?
we show that there is only one inverse of each number?
I mean,
Uh, um,
the inverse is unique.
Inverse is unique. Yeah, I think we can show, no, because we had ax plus by is equal to 1, right?
Yeah.
As long as ax plus py, actually, ax plus py is 1. So you'll have ax mod p is 1. So no, actually, it is not necessary to be unique. I think if it is prime, it will be unique. No, actually, it is not necessary to be unique, I think, because this has multiple solutions, if you remember, right?
Yeah.
Like when we used to say that GCD, from the GCD Euler's algorithm division lemma, you got this, there could be multiple solutions,
Yeah. I would like.
right?
Yeah.
So it might be possible that X could be many other X's are also there, but so far we have not seen a case where that is happening. I think for composite numbers it might happen when you're doing p is not prime, but I'm not sure about that. I don't think it will be unique. It might not be unique. I'm not sure. But right now what I'm trying to say is in this set we can group together terms that are inverse of each other, right?
Yeah.
Right. So if you group them together, right,
Yeah.
you are getting a situation where uh, there are some pairs which have different numbers and some pairs which have the same numbers, right?
Yeah.
So the case that we want to focus on is this 1-1 case and the 10-10 case, which is saying when is A the inverse of A, right?
Yeah.
When is A going to be its own inverse, right? So that means A into A should be 1 mod P, right?
Yeah.
A square should be 1 mod P, which means A square minus 1 should be 0 mod P, right?
Yeah.
Which means P divides A square minus 1, which means P divides A minus 1 into A plus 1, right?
Yeah.
Which means A should be plus minus 1 mod P, right?
Yeah.
Correct.
Yeah.
So notice that 1 is 1 mod 11 and 10 is minus 1 mod 11, right?
Yeah.
So in those cases, you are getting uh, the situation that some number is inverse of itself, right?
Yeah.
So now what we will do is we will multiply all of these numbers in this set, right? And take mod 11 here, right?
Yeah.
But when we multiply, we'll multiply in such a way that we group them together like this, right?
Yeah.
So what will happen here is if I do 1 into 1, 2 into 6, 3 into 4, 5 into 9, 7 into 8, and 110 is there. And we do mod 11, right?
Yeah.
We get 1 here, 1 here, 1 here, 1 here, and 1 here. And this is minus 1, right?
Yeah.
So what we are getting is minus 1 mod 11, right?
Yeah.
And when you multiply everything from 1 to 10, you are getting 10 factorial is equal to basically minus 1 mod 11,
Yeah.
right?
Yeah.
Correct. So what we can say in general is if let P be a prime, then P minus 1 factorial will always be minus 1 mod P. Why? Because if P is a prime, my set S will be what? From 0, 1, 2 till P minus 1, right?
It does not include
So it
0.
doesn't include 0, right? All the remainders from 1 to P minus 1, right?
Yeah.
And then if you multiply all of them, what we will do is we'll take 1 and we'll take 2 and 3 and so on till P minus 1. And we will be able to find numbers here which will be in inverses of each other, right?
Yeah.
So how will we prove that you will get always minus 1 mod P? How can you prove that this product will always happen like this?
Because like we can find pairs.
So for any X here, can we find a pair here is the question, right?
Yeah.
So for any X, can we find the inverse here? So 2 for any I here, let's say, I into X is equal to 1 mod P. So we know that it is guaranteed that there will be an X, right?
Yeah.
It is guaranteed that there will be an X and that X will lie in this set.
Yeah.
That X will lie in this set is also guaranteed because we have Ix plus Py is equal to 1 because X and
P co-prime.
I and P are co-prime, right?
Yeah.
I and P are co-prime, so there is an X, right?
Yeah.
And that X is going to be in this set, right? Correct.
Yeah, because this set contain every
All the
possible.
possible remainders, right? Correct. So for each number, we will find a pair. The only special cases will be the 1 and p minus 1 because they are 1 or minus 1 mod p, right?
Yeah.
Every other number will have a pair. Also, because it is a prime will be odd, and odd will means that 1 to p minus 1 will be even number of terms here, right?
Yeah.
So these terms will be even, so you'll be able to pair up, right?
Yeah.
And therefore you will ensure that all of these products become 1, and therefore you'll get p minus 1 factorial. The only thing that will be left is 1 and p minus 1, which will be minus 1 mod p, right?
Yeah.
So this is your Wilson's theorem. This is Wilson's theorem that for any prime, p minus 1 factorial is always minus 1 mod p, right?
Yeah.
Now, another way to check prime number is basically for any integer n, for any integer n, we have n minus 1 factorial is congruent to minus 1 mod n if and only if n is a prime. So if you are getting a situation that n minus 1 factorial is minus 1 mod n, then that means n is a prime. So that is another test by which you can check whether you get a prime number or not. You have a prime number or not.
Yeah.
Right.
How do
Now,
you prove the only if part?
only if part, uh, basically you will have to, for if part is easy, right?
Yeah.
If n is a prime, we can prove this. Then the only part I'm not sure. Uh, it means if and only if means double implication. That means we have to show that this implies prime. Okay, okay. We know this side, right?
Yeah.
If it is a prime, we can show this, right?
Yeah.
We have to show this side that n minus 1 factorial is congruent to minus 1 mod n implies n is a prime.
Oh, I know already. I think because like if n is not prime, there's a divisor of n within 1 to
Yeah,
n plus 1, and
yeah,
then
yeah.
it's 0.
0 will come, right?
Yeah.
If n is not a prime, as soon as you write the set, right, n minus 1 factorial, there will be other divisors which will make this 0, right?
I think so.
Yeah,
I
yeah, for sure. Because what will happen, no, no, 1 second. Let's take a case, no, let's take n is equal to 6, for example, right?
Yeah.
So 5 factorial, we have 5 factorial is congruent to minus 1 mod, no. Oh, no, no, we can't take an arbitrary case, right? We have to get a case such that this is true, right?
Yeah.
And from there, we have to show that it is prime. Okay, we can assume the opposite, right? Assume that this is not true. No, no, that won't work. Uh, from here, we have to prove that it is a prime. Okay. No, what you were saying, no, it will not work because that is proving that is proving this side, I think.
Yeah.
Right? Like it's almost like we have already assumed it is a. if n is composite, what happens to n minus 1 factorial? Let's just think about that. If n is 6, so 5 factorial, right? It is 1 into 2 into 3 into 4 into 5, right?
Yeah.
Now, mod 6, if we want to do, right? Uh,
0.
this is actually coming out to be 0 mod 6, right?
Yeah.
The reason that is happening is that this and this multiply and get 0 mod 6, right?
Yeah.
So can we prove in general that n minus 1 factorial will always be divisible by, no, not necessary. Oh, I think what happens no is, say if you have a composite number, all the numbers before it is in n minus 1 factorial, right?
Yeah.
So that composite number has some prime factorization, no?
Yeah.
And the numbers before it, all those prime factors are already present.
Yeah. 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 Yeah.
Like the prime factors are already present there before it, no?
Oh, yeah.
That is what is making it divisible,
Oh, yeah.
right? Like, the situation will be slightly different for numbers like 27, which have 3 factorial, 3 cube is the prime factorization, and 1 to 26 if you do, okay, again there will be enough number of times that 3 will come, right?
Yeah.
You understand what is happening?
Kind of.
The prime factors are already going to come many times before, right?
Yeah.
So the number is already constructed. N minus 1 factorial will always will be divisible by n.
Yeah.
Because n's prime factors will definitely appear before. No? So, because, I mean, I am also not fully sure, but it feels like that is the reason, right?
Yeah.
Uh, yeah, I'll think about it. Maybe if I get a proof, I'll show you in the next class. Uh, one side is easy, the other side is not so easy to prove. But the theorem is true, okay?
Yeah.
N minus 1 factorial is minus 1 mod n if and only if n is prime. That is your Wilson's theorem. Then the next thing that we have to look at is Euler's theorem. And in this, we say that let mod of S be the number of elements in S. And S is the typical set of all the non-zero remainders, right? Correct. Now, when we are doing S is the reduced residue class for N. Residue class for N. And now notice that we are using N, not P, right? Euler's theorem is applicable for N. Okay. Not generally for a prime number only, right? So
Yeah.
S set is basically 1, 2, 3 till N minus 1, right?
Yeah.
Okay. So now, if you take the set AS set is what? A, 2A, 3A, and so on till N minus 1 into A. Correct. Now, what we can say is this set is equal to this set. We have shown that as long as GCD of A and N is equal to 1, right?
Yeah.
As long as GCD of A and N is 1, you will always have AS set will be equal to S set mod N, right?
Yeah.
So again, we multiply again here. So A into 2A into 3A into N minus 1 into A. should be congruent to 1 into 2 into 3 till n minus 1 mod n, right?
Yeah.
Now, mod S was the number of elements in S. So you are doing a power mod S here, right? And n minus 1 factorial, right?
Yeah.
A power mod S n minus 1 factorial is congruent to n minus 1 factorial mod n, right?
Yeah.
Hmm. One second. This is product of Can we cancel right now?
Cancel n minus 1 factorial.
Can we cancel?
Right? Then if n is not prime, we cannot cancel, right?
If n is not a prime, for example, we can't cancel if n is not a prime. So, one second, let's think about this. Okay. I think we can't cancel right now. We'll have to think of a different way to do this. Uh, let's introduce the phi function. Phi function basically is called the totient function, and the definition of that function is it is the number of integers between 1 and n that are relatively prime to n. Right?
Yeah.
So phi of n is equal to number of integers a such that 1 is less than equal to a is less than equal to n, and GCD of a and n is equal to 1, right?
Yeah.
Now, this is called the Euler's phi function or totient functions, Euler's phi function. Now, let's take some cases. So, for example, if n is equal to prime, right? Phi of n would be equal to what? P is a prime
One.
number. So it will be p minus 1, right?
Yeah.
Because it will be from 1 to p minus 1, correct?
Yeah.
Okay. Now, let's find out some special cases. For example, let's make a table here. Your n is here and phi of n is here. And we find out n is 1, then phi of n will be 1, right?
Yeah.
N is 2, phi of n will be 1,
Okay.
right?
When n is 1,
Hmm.
phi of is it 1?
Because it can be equal to 1.
Or then for 2 it is also 1.
Because it can't be 2, right?
Oh yeah.
GCD of 2 and 2 is 2, right?
Yeah.
Correct.
Yeah.
And 2 is a prime, so it will be this, right? When
Yeah.
it is 3, it will be 2, right?
Yeah.
When it is 4, what will it be?
1, 3, also 2.
And 5, it will be 4, right?
Yeah.
6, it will be
1 and 5, 2.
so 2. So you can figure out what n and phi n is, right?
Yeah.
Correct. So now we will be using this Euler's phi function, and we'll be proving this theorem. The theorem is this: if GCD of A and M is 1, right?
Yeah.
Then A power phi of M is congruent to 1 mod M. We'll be proving this now. Okay. So GCD of A and M is 1, and we want to show that A power phi of M is 1 mod M. Correct?
Yeah.
So if GCD of A and M is 1, then the numbers B1A, B2A, B3A, and so on till B phi of M A mod M are the same as B1, B2, B phi of M mod M. Although they might be in a different order, these are the same numbers.
What's B1 and B2 and so on?
So B1 and B2 are the different possible remainders that come when you do mod M, right?
Yeah.
So if B is relatively prime to M, then A into B is also relatively prime to M, no?
Yeah.
Because A is relatively prime to M, right?
Yeah.
So just just think of these numbers, like for now, just these are just different numbers. These numbers and these numbers, the difference is just it has been multiplied by A, right?
Yeah.
Right. So what we are saying is if B is relatively prime to M, then AB is also relatively prime to M, right?
Yeah.
So if we have a list of possible remainders with M here, B1, B2, right?
Yeah.
This might not be the total. This is not going up till BM, right? This
Yeah.
this is some subset of the possible remainders, right?
Like, but which numbers do cancel out?
We will discuss that. Just hold on for a second. Somebody is at the door. I have to go check. 1 second. Yeah, sorry. So what we are saying here is there are some numbers in the set mod m, right?
Yeah.
Which are such that if you multiply them, and they will be the remainders that are co-prime to m. So, for example, let's take an example and understand this. So, let's say you have you want to do modulo 10, right?
Yeah.
And the possible numbers for you are 1, 2, 3, 4 till 9, right?
Yeah.
Now, you will not multiply all of them. What we will multiply is all the numbers which are prime to 10, right? Or
Yeah.
basically, we want to list out all the numbers in phi of 10, right?
Uh-huh.
So which ones are there? 1, 3, 7, 9, right?
Yeah.
So just take out 1, 3, 7, and 9, right?
Yeah.
Correct. Now, these numbers, if these numbers are taken mod 10, right?
Yeah.
And you want to say, you want to use the result a power phi of m is equal to congruent to 1 mod m. Here m is 10 for you, right?
Yeah.
You have to choose a also, as which is GCD a and m is 1, right?
Yeah.
A can be any number. A can be 7, for example.
Okay.
GCD of 7 and 10 is 1, correct?
Yeah.
So what you will do is multiply each of these with 7. So 7 into 1 is 7 mod 10, right?
Yeah.
3 into 7 into 3 is 1 mod 10, right?
Yeah.
7 into 7 is 9 mod 10, right?
Yeah.
And 9 into 7 is 3 mod 10, correct?
Yeah.
So what you are saying is B1, B2, B3, B4 was such that when I multiplied by A, AB1, AB2, AB3, and AB4 are also same, right?
Yeah.
7193. And this was 1379, right?
Yeah.
Just the order has been changed, right?
Yeah.
So now you can say that if I multiply 7 into 1, 7 into 3, 7 into 7, 7 into 9, I would get what? 7 power 4, 1379, right?
Yeah.
On one side, and on the other side, 1379 mod 10, right?
Yeah.
And now you see, like when we were doing the previous case, we got some n minus 1 factorial. No, that was wrong. We have to only select the divisors that are, select the numbers that are co-prime to n, right?
Yeah.
So now I can divide this and this, right? Because they are co-prime to 10, all of these.
Yeah.
And now you get 7 power 4 is equal to 1 mod 10,
Yeah.
right?
Yeah.
So basically, what is happening? Fermat's theorem was telling us that we had a power p minus 1 is 1 mod p, right?
Yeah.
Where a and p had GCD 1 and
Yeah.
p was prime, right?
Yeah.
Now, Euler's theorem is telling us if p is not a prime, right? Do you have some a power something which is also 1 mod m, right?
Yeah.
Correct. So is there some power of A? Here also GCD A and M is 1, right?
Yeah.
Is there some power that you can raise A to? You can raise A to in order to get 1 mod M, right? And M is no longer a prime here.
Yeah.
M doesn't have to be a prime, right?
Yeah.
So you can easily see that this format Euler's theorem is in a much more general case, right?
Yeah.
Right now we got 7 power 4 is the number that is 1 mod 10, right?
Yeah.
So it is very similar, except here, since it was prime, we multiplied all the numbers in the set 1 to p minus 1, right?
Yeah.
And here it was not a prime, so we multiplied only the numbers that are co-prime to m, right?
Yeah.
Correct.
So how do you prove the like the 1379
Hmm.
times 7
Hmm.
they are the same set?
We proved it, no? We got uh, 1379 mod 10, right?
Yeah.
And 7 times 1, 7 times 3, 7 times 7, 7 times 9 mod 10 is also going to be same.
Yeah, but like how do we prove they are the same?
In this case, the numbers are obvious. It is the same, right?
But like for
In general, we will prove it. Uh, the general proof is going to be the same. You will take two. You will take two of them and show that the subtraction is not divisible. Like, suppose we take two numbers from our list, BJA and BKA, right?
yeah.
And we know that A and M are co-prime. So if we can say that they are equal, suppose they are equal, right? Suppose they are congruent, or BJA is congruent to BKA mod M, right?
Yeah.
If they
So
are congruent, that will imply that Bj minus Bk multiplied by A is congruent to 0 mod M. So that means M divides Bj minus Bk, right?
yeah.
Which is not possible because B1, B2 and all are going to be lesser, right, than your M,
Yeah.
because they are from the set of remainders, no?
Uh-huh. Yeah.
Like this is a smaller set. This is a subset of the set of remainders from mod 10, right?
Yeah.
You can never get Bj minus Bk is going to be divisible by 10.
But like so also like for any BJA, we don't get a number that that is outside the subset, like 1379.
Um, we don't get a number that is outside the subset. What we are saying is, see, 10 had how many remainders? 1, 2 till 9, right?
Yeah.
Out of these, for format or for Euler's theorem, we are only selecting some which are co-prime, right?
Yeah.
Co-prime to 10, right?
Yeah.
So then what do you mean now?
I mean, like for any BJA, we don't get like 2 or 5 that are not co-prime to 10.
Uh, we are anyway not putting those. So BJA would be one of the co-prime ones, no? And BKA would be one of the co-primes ones, right?
Yeah.
So we are selecting 4 out of the 9 possibilities here. 1, 3, 7, 9. Now, using just these 4 and multiplying it by A and all will give us the Euler theorem. I'm not properly understanding what you're asking, but are you understanding what I'm saying?
Kind of.
Like, see, if we just recall the Fermat's theorem, how we got. So, Fermat's theorem, we used all of them, right?
Yeah.
We used all of them because it was prime number. So, there are p minus 1 of them, right?
Yeah.
Now we are using a smaller set. How many? Phi of n. These many we are using.
Yeah.
right? So whatever was working for Fermat's theorem, same thing will work here also, except you have a smaller set of numbers, right? And you're
Maybe.
using those numbers only because at the end you want to divide by that, right?
Yeah.
So, like for me, I don't think there is any problem here right now.
Yeah. I think I understand. Because like
Huh.
just now I was wondering, if we times 7 and 1,
Huh.
we
Huh.
get like 2 or 5, like that are outside the subset
But
1,
it's
0.
not possible, right?
Yeah.
Because 7, when you do A into mod 10, uh, when you multiply by A, we already had A and 10 were co-prime, right?
Yeah.
So if you are getting 7 into, oh, you're saying if 7 into 1, it is possible to get a 2. Okay, okay. 1 second. I understand your question now. You're saying, is it possible to get some other remainder not of this set
Yeah.
after multiplying by A? Uh, hmm. Uh, let's take another example. Let's take a number M is 9 and A is 5. Okay. So the full set of remainders is 1, 2, 3 till 8. The set of remainders that we will be using is 1, 2, 4, 5, 6, 7, 8, right?
Yeah.
These are the 6 remainders that are co-prime to 9, right?
Yeah.
And if you do 5 into 1 and 5 into 2 and 5 into 4, 5 into 5, 5 into 7, 5 into 8, right? We are
Yeah.
getting 5, 1, 20 is 2, and 25 is 7, and 35 is 8, right?
Yeah.
And this is 40 is 4, right?
Yeah.
So again, you're getting 5, 1, 2, 7, 8, 4, 7, 8, 4. You're getting the same ones. So why are we not getting 3 and 6, 3 and 6, right?
Yeah.
That is the question. From here, we can easily get the result. We can get that 5 power 6 is going to be congruent to 1 mod 9, right?
Yeah.
Because we can now divide by 1, 2, 4, 5, 7, 8, right?
Yeah.
But why is it not coming in that set? Okay. Uh, Whenever you multiply A times some remainder here, let's say B1, and A is congruent to A is co-prime with M. A and M co-prime. So if I multiply two numbers, none of which have any common factors with M. Oh, now it is obvious, no? See, what is special about these numbers? These numbers have no common factors with 9, right?
Yeah.
Correct?
Yeah.
And what is special about A? A is also having no common factors with 9, right?
Yeah.
So when you multiply two numbers which have no common factors with 9, you should end up having another number which is part of the same set, no?
Oh.
Right?
Ah.
Like
Yeah.
if both have no common factors, then still there is no common factor, right?
Yeah.
So it will always be a part of the same set, right?
Yeah.
Clear, no?
Yeah.
Yeah, okay. Then what we need to figure out. So far what we have gotten is this result, that there is a formula, Euler's formula, a power phi of m is congruent to 1 mod m, where a and m have 1 GCD, right?
Yeah.
This is understood how it has come out.
Yeah.
Okay, fine. So this is a useful result, but the problem is that we can't use it much unless we know the value of phi of m properly, right?
Yeah.
We need to be able to find phi of m. Then only we'll be able to use this result, right?
Yeah.
So far what we know is phi of p is equal to p minus 1 if p is a prime, right? Correct.
Yeah.
Uh, can you find out what is phi of p power k?
People.
Think about it. What will be phi of p power k? Phi means what? Phi is number of numbers from 1 to m such that co-prime to m.
It's p to the power of k minus k.
Slightly wrong, but think about it. The answer is this, p power k minus p power k minus 1.
Wait, so we cancel out like p to the power of 2, p to the power of 3,
Hmm.
and so on.
So basically, phi of p power k when is a number a not relatively prime to p power k? So factors of p power k, factors of p power k are p, p square and so on, right?
Yeah.
Till p power k, right? So a is not relatively prime to p power k when it is divisible by p, right?
Yeah.
So, okay, so if I want to calculate phi of p power k, I will say the total number of numbers from 1 to p power k. The number of numbers will be p power k minus, this is total number of numbers, right?
So we count like p, 2p, 3p
Ah,
until p to the power of k. And so it's p to the power of k divided by p.
correct, correct. Minus all the factors. So those will be p, 2p, 3p, and so on till p power k minus 1 minus 1 into p, and then p power k minus 1 into p, right?
Yeah.
These are the factors of p power k, right? Which we want to remove, right?
Yeah.
So the sum of these numbers would be p power k minus 1. You can check that. The number of factors here.
Yeah.
Because it is 1 into p to p power k minus 1 into p, right?
Yeah.
So phi of p power k is coming out to be p power k minus p power k minus 1. right?
Yeah.
So that is our second result. So far we know first result was phi of p is p minus 1. Second result is this. So for example, now you can find phi of 2401, for example. What is that? So check the prime factorization of 2401. It is phi of 7 power 4 actually, this
Yeah.
is,
Yeah.
right? And
Yeah.
that would be 7 power 4 minus 7 power 3, right?
2401 minus 343.
Hmm. It would be 2058, correct?
Yeah.
Then now what we want to find out is we want to find out phi of m when m is not, when m is normal product of prime powers, right? Product of prime powers. Like any number can be written as product of prime powers, right?
Yeah.
So if m is basically p power j and q power k, where p and q are primes, right?
Yeah.
We want to find out this phi of m, phi of p power j and q power k, right?
Yeah.
Now, here we will learn that phi function is the first example of a function that we have seen that is a multiplicative function. Multiplicative function means generally it satisfies this kind of property. F of mn is equal to f of m into f of n. Okay. So phi of p power j q power k will be equal to phi of p power j and phi of q power k. This is a statement right now. We will prove it. Okay. So for now, let's just check it for some small values, right?
Yeah.
Like first, let's check it and confirm whether it is coming or not. And then we'll try to prove this. So let's say phi of 14 you want to find out, right?
Uh-huh.
So normally you can find it out directly, right?
Yeah.
Directly, if you try to find 14, number of numbers which are not divisible, co-prime to 14. So 1,
3, 5, 9,
3, 5,
11, 13.
6, 7, 8, 9, 9, 11,
13.
13. That's it, right?
Yeah.
So the number is coming out to be 6, right? And now we'll say that let's split it as 2 into 7 and let's check whether this works out or not, right?
Yeah. So it's 1 times 6.
1 times 6, right? So this method is also seeming to work out here. Similarly, phi of 15, we can guess it is phi of 3, phi of 5. So it should be 2 times 4, so 8, right?
Yeah.
Now we can list it out also. 1, 2, 3, 4,
7,
5, 6, 7,
8,
8,
11,
9, 10, 11, 13. That's
14.
it.
14.
14 also, right? Yeah, 14 also. So it is coming 4 and 4, 8, right?
Yeah.
So right now what we are getting is it is working out. So now our guess is that the result will be this. If so, notice that so far we are doing phi of prime powers, right?
Yeah.
We are guessing that this is true. But notice one thing, that P and Q have GCD 1, right?
Yeah.
Because they are different primes, right?
Yeah.
So maybe the result is if GCD of M and N is 1, then phi of Mn is equal to phi of M into phi of N, right?
Yeah.
Correct. So this is what we want to prove. That if GCD of M and N is 1, then phi of Mn is phi of M into phi of N, right?
Yeah.
Okay. Uh, let's think about it.
Oh,
Hmm.
so there's no number between 1 and Mn that
Hmm.
both a multiple of M and a multiple of N.
There is no number between 1 and Mn, which is
Both.
both. Hmm. Right now, here we are calculating numbers from 1 to Mn that are not divisible or that are co-prime to Mn, right?
So we're suggesting that the M and N are some like powers of prime,
Hmm.
or Mn are any number.
I think we should have first tried to prove this because I think this is a slightly more general statement, right?
Yeah.
Uh, I have to think. I have not thought about the proof yet. So the first set, this set, right? Phi of Mn, right? This is the set of numbers, let's say A, such that 1 is less than equal to A is less than equal to Mn, and GCD of A and Mn is equal to 1, right?
Yeah.
Correct. Uh, the second set is what? Second set is if this is called A and this is called B and this is called C, the second set is pair of numbers BC such that 1 is less than B is less than M and BM GCD is 1 and 1 is less than C is less than N and CN GCD is 1, right?
Yeah.
We have to show that these two sets are equal, right?
Mhm.
Or actually we have to count, right? Count the number of elements, right, in these sets. Because phi of Mn is not a set, it is the number of elements in this set, right?
Yeah.
And here, phi of M is the number of elements here, right?
Yeah.
And phi of N is number of elements here. And the product of those two numbers will be the total number of elements here, right?
Yeah.
Okay.
So if
Uh,
Mn are prime, it's very easy to prove.
if Mn are prime,
Yeah.
then phi of M will be P M minus 1 and all. And this will be N minus 1, right?
Yeah.
and m minus 1 into n minus 1 you get there. No, I'm saying wrong. If they are prime, just simple primes without powers, then it will be that. I'm still thinking. You also keep thinking 1 second. So what we want to show is that number of elements here is equal to number of elements here. So it will be enough if we can show a one-to-one correspondence, right?
Yeah.
Basically, if we can show that one element of this can be assigned to one pair here, right?
Yes.
Correct, no?
Yeah.
Then the number of elements on the set has to match, right?
Yeah.
So, okay. We want to take one integer in the first set and send it to some pair b comma c in the second set, where
I think counting the number of elements that are not co-prime to Mn is easier.
not co-prime to mn.
Then we just minus.
Mn minus.
Yeah.
That might be easier. Yeah. Okay. Yeah, I'll have to think about it. Maybe we'll stop at this point and let's try to work out this proof. Or I'll try to find if there is some easy way to do this. But right now, I'm not getting an idea of how to set up a correspondence. I want to show that A such that 1 is less than equal to A is less than Mn. GCD of A Mn is 1 maps to some B comma C such that 1 is less than B is less than equal to M. GCD of P and N is 1. 1 is less than C is less than M. N. GCD C and N is 1. Can we make a relation between element here and element here? So here we have A mod Mn. We say A mod Mn. Set of elements of A mod Mn. Okay. Uh, hmm, not sure. Okay, I'll try to do this and figure out what is supposed to be done here. And if we get that property, phi of Mn is equal to phi of M and phi of M, then we can do anything because we know how to do prime factors, right?
Yeah.
Like phi p per k is p per k. together with this property, we can now calculate phi for anything now. We
Yeah.
just need to show this property, then we will be able to calculate phi for anything, and then we can use this result, Euler's result, easily. So I will look at it, this proof, and tomorrow we'll discuss this.
So I have an idea. So like, for example, we say m is some p to the power of I. Then n is like another like p2 to the power of j, such that like p1 and p2 are prime.
Now p and q are prime, let's say.
Then we count the number of multiple of p and the number of multiple of q that are smaller than mn.
So number of multiple which are smaller than I and j.
Yeah.
So
So
which are factors of this, right? So
yeah,
we can say you are doing this side or this side? This side, right?
Oh yeah.
So divisors of this. So we can say P, P, PQ.
I think it's P2P, 3P until Q to the power of J minus 1P.
P,
and
2P, 3P.
Until Q.
And you'll have to do Q also same time, no?
Yeah. And Q to Q until P to the power of I minus 1Q.
But there could be numbers which are PQ and all, right?
Yeah, so we count that also. And
yeah, so direct counting, what you're trying to do may work, but the problem will be that like you'll have to take so many cases, right?
Oh yeah.
You understand that M and N, if it is like a P, I, Q, J is M and N is Q, R, S, T. S is also prime or something, right?
Yeah.
It will be more annoying than like if you try to do direct counting, it will be difficult to prove because there are so many cases, no?
Yeah.
Because right now we don't know whether M is having one prime or multiple primes or N is having one prime or multiple primes. So that is why I am not trying to do the direct count because it will be annoying. We have to think of some way to prove that every element of this set is mapped to this element, some element of this set, some ordered pair. So that is what I will try. Right now, I'm not getting the idea. Maybe there is some easier proof or something. We'll check. Okay.
Yeah.
And tomorrow's class will not be so much theory. It will be more problems because most of the theory part we have covered almost. A little bit of theory is left, but that will be next week. So we'll finish this part off and then we'll do problems. Okay.
So how many theories do we left?
Not much is left. Like in number theory, at least we have to do Chinese remainder theorem after this, and after that, I don't think we need to do anything else. We just need to practice problems.
Okay.
Chinese remainder theorem and a little bit of Diophantine equations.
So these theories will allow me to do most number theory.
Yeah. Whatever we have done so far, basically Fermat's, Euler's, Wilson's theorem, this phi function, and Chinese remainder theorem we'll do, and a little bit of Diophantine equations. So that is more than enough for any Olympiad, at least national level Olympiads will not ask theory more than this. The key thing would be to apply them in different problems. So the theory part will be over by next week for sure.
Okay.
After that, it's about doing more types of problems and all. Okay. Uh, we'll discuss tomorrow then. Hello?
So yes.
Yeah. So we'll continue from this point tomorrow. Okay.
Okay.